Hello hackers, welcome back to our Hacker series. This is going to be the 10th project in our series, and we have already done 9 projects and a group of that was exclusive for Windows, not Windows, web application security related projects. And today we are going to deep dive into the asynchronous programming and threading. So I already did one async programming for the LLM tool that I developed in this series. So in that video I already mentioned that we will be doing a detailed threading and asynchronous project in later videos, and this is that video that I mentioned earlier. So we are going to develop a port scanner that we are going to implement in different ways, like normal way, in the threaded way, and using asynchronous design pattern. Then we go for the real practical way of how to control resources and do it asynchronously using the Semaphore design pattern. And as I mentioned already, the socket programming part I'm going to do it a bit faster because I'm planning another video for socket programming exclusively for that networking part. So in this video I'll be concentrating more on the threading and asynchronous programming part. So let's start our project. Cargo new. Okay, name it as port scanner, and just move to that folder, open our IDE, and for this one, as I said, we are going to make use of REST socket programming a bit. So we will be using socket address and TCP stream for our network connectivity, and we will be accepting some parameters from the user side, so that we are going to set it as command line arguments. So we will be making use of that. And now we need to define our port scanner and say scan port, and I'm saying IP as this is fine, and I'm saying 16 integer and an IP string referral. Let the address equal to, we can make it in a different way, format. What I'm planning is just to set it as normal. This one is very annoying. Sometimes these AI suggestions are really annoying, sometimes it's very helpful also. So what's going to happen here is, see, it just made the IP, combined the IP and port, and because its socket address needs a format of IP : port number, so we just made it like that, and we need to convert this to socket address. Why? Because I'm going to make use of a function that is a connection with timeout. It's not going to be a normal connect function, because normal connect may take some more time in performance basis. So I'll be making use of connection with timeout function. For that, it accepts a socket address. That's why I'm going to convert this to socket address instead of unwrap. Actually, if you want, you can make use of expect with a message saying invalid address in case of any issues with the address. So now we have the socket address. Now the next thing we can try is we can connect timeout. One more thing we need is we need to analyze the performance of the duration of the port scanning to analyze to find out what's the best option for us. So I'm just making use of the duration. So what I'm going to do here is Either you can directly connect here, and it's going to be the reference to the address, and the timeout, actually we have to define the timeout now. So for that, I think it's better to define the duration from seconds. Oh, this came by default here. And what this one is doing is actually connect timeout. If you check, it returns a result type. So this function makes sure that if the result is suppose if the connection timeout is not, connection is established successfully, in that case is okay returns a boolean value. That's if it's true, that means it got connected to the target and we can confirm the connectivity. If in case if it returns false, means somehow the port is not opened, so it didn't get connected, or the port got closed. So that's why this is a handy way to confirm using a boolean. So it will be easier, or it will be logically really good in a way when we call from a main function, we can check whether that port is opened or not. So the next thing that we have to do is we have to ensure we have to get the parameters from the command line to make it easier from here. So what we can do is this one we already did actually. If you don't know what exactly we are doing, I strongly recommend to go to the initial videos, and most of the videos we were doing the same thing. So see, the A is already suggesting that let just take the arguments in a vector of string, then just say the first one is IP, and the second one let's say let port range or something. Okay, you can say port range, and the port range is always it's like what I'm planning is like, from the user perspective, we just say some symbol like hyphen or something. Just say, imagine we are going to do it like 1-2 or 1-100 means all the ports within this range. So what we can say is, the suggested way is not exactly. It should be, we have to split the argument, then you have to take the first and last. So the best way is always second part of that with a split. See, this one is really annoying. This is why people are moving away from this VS Code and doing the Vim code, Vim editor. So so what is thing that we have to do is we have to split this up, split it, just say hyphen. So after splitting it, we are going to take all the arguments, and it's going to be so not this one, it's going to be, let it be like a vector of of course this is going to be a vector of this. So there's nothing but we just took when the from the command line, what we are going to do is we are going to supply the IP, then the port range using the hyphen. So it is just taking that into a vector of string reference. That's it. So this one is really good. It identified that. Let the start port be port range of 0 road pass. This one is good. This is really good. It's suggesting a lot of stuff. Let me consider that. End port is port range of the first argument. From this, and we are taking that. So seriously, this is really good. So for this one, I'll just try to say both sides, like whether the port is opened or closed, instead of just saying port is open. So we are calling the scan port, and if it is successful, we just made it very specific that if we don't wait for more than 1 second, and if it is going to take more than 1 second, this will return false, and yeah, we say the port is closed. So basically this is correct. For the safety check, we just say if here, if the just long, yeah, let it be not equal to 3, then println usage is IP port range, yeah, is correct, then return. Now I think it is ready, our port scanner is ready. So go to terminal, cargo build, it's finished. cd target debug, yeah, it is there. Let's run the port scanner. Yeah, it says it needs these things to run it. So I'm going to give my other machine's IP here for testing, and it has an IP of 1.64. is my practicing VM, so let it be 192.168.64, and as a port range I'm going to give 1 to 100. Let's see what happens. Oh no, we didn't calculate the time, in fact, so we had to calculate the time before the ports can start. So what we can do is let start time equal to instant dot now, and after this loop we say duration equal time elapsed and print scanning completed. That's really good. It suggested some very sensible ones. Build it again, cargo build, say cargo format, yeah, format well. Now we are going to build it again. So let's say start the scanning again. Port is closed, 2 is closed. See, this is because we just said this message. I mean, we mentioned this one. If we don't mention this one, this message will never print. So what to do to make it faster? I'm just breaking it here. So just say 75 to 85, because I have some ports open in that range. 75, 76, 79. See, 80 is open, and 84. See, it did take 10 seconds. It has several reasons. One is because we have set the connection timeout as 1 second. So definitely, if the port status is success, like if the connectivity is there, it checks on that interval. Like if there is no connectivity, the good thing is that within if the target is not reachable within 1 second, or that network activity is not responding, so that terminates there and you get the result. That's why we use the connect with timeout method. So now for 10 port, I mean, just for scanning 10 port, it did take 10 seconds. Maybe for smaller machines, like smaller targets or small set of port ranges, this is fine. But in a large scale, when you think about this one, is of course it's not going to work. And just remove this method, this print, and we just build it again. Do it again. See, now this is why I did print the port closed status. See, now, yeah, the same 10 seconds is taken. So if you try to increase the number of ranges, the second number of seconds will be more, because the target is there. So definitely it's going to do the check the status of the port, and it seems that every scanning attempt is taking 1 second. So in a practical way, definitely this is not going to work in a real-time scenario. This is really useful if you do it in a synchronized way, just for small ranges. Even the 10 seconds are really for 10 ports, for 10 seconds is really it's not scalable, in fact. So what we can do is we are going to make use of threading in Rust. So let me come back here, and what you mean by thread is actually is like OS level constructs managed by the operating system, and each thread has its own stack that runs independently. That's the main thing. Like when you create a thread, it has its own stack on in it. It doesn't matter which OS you are going to use. Every OS is going to make its own stack for the thread. So when you create a thread, like in Rust, we are going to make use of using thread.spawn method. The OS allocates resource for this thread. It is going to allocate memory, is going to set up the CPU time, and runs in parallel if you have multiple cores. Like, it depends on your machine. And this is handled by the operating system. Actually, this is not going to handle by the Rust ecosystem. It's completely the operating system that take care of the threads. And of course, this is really heavy because depends on the operating system. Actually, it has a minimum level of memory. I think in Windows is 1 MB and in Linux is 2 MB. So definitely it's going to it is scalable to some extent, but in a resource consumption way. Like if you are going to run this scanner in a very low resource Linux server, definitely it's going to get crashed, or it is not going to work high, because it is going to make use of, every thread is going to make use of the minimum level of memory that we set, and the CPU usage will be there. So anyway, what we are going to do is we are going to convert this normal synchronous application to multi-threaded application. So we are going to see the difference between these two, like how it differs in performance ways. So let's create a multi-threaded port scanner. For that, let's go back to the code. Just say, so basically for a multi-threaded port scanner, try to keep this scan port as a same function. Like so we are going to call it from different threads. That's the only difference. Before using the thread, we have to use the namespace called library. What is called in this one? Library. I forgot that. The package. It's a standard part of the standard package in Rust. We're going to make use of the threading package, and let's say, okay, what to say? Not scan ports again. Multi-threaded scan. oh here, yeah, it suggested the actually very necessary parameters. Let's see what, just I'm going to see the tab and see what happens here. So this is very important here we need these handles, and just see the difference here is going to be mutable because we are going to update the handles. So every port in from the start port to end port range, here is another thing that you have to, when you are going to use of threading is going to make use of the same technique, same ownership rules that Rust is having. The Rust has only one ownership rule, that is only one owner at a time for a variable, for any variables. So you should be very careful on that. Actually this has done like it did a lot of coding for us. This is really an effective way. We're going to shadow the same variable here. We are going to shadowing it and taking control of this variable and moving that entire variable ownership to this thread. When we are going to call this thread, thread.spawn is going to create a new thread by the operating system, and it's going to have its own memory, its own CPU time, everything will be separate for this thread, and then it is going to call the same method. See, this is very improved. So it did take the same thing that we did here to here. Okay, whatever it is. So what happens here is every thread, when you are calling with the thread.spawn, it returns a handle. So we are collecting that handle and we are keeping the handle inside a vector. Why? Because we need to iterate over the handles, and we have to call this method handle.join, because this will post the main thread and it waits for all the threads to be completed from this function. So what happens here is when we are going to call this function from the main thread, so this one we are going here to comment out this one. Oh yeah, it's suggesting that. So when the call is going to be in this multi-thread scan, what happens here is it inside this for loop we create a bunch of new threads using the thread.spawn, and these threads are going to create a post on the main thread, because we are calling this handle.join. So what happens here is until all the ports get scanned, the main thread will wait. So once every thread is finished, the control goes back to the main thread and it continues. So here then after the thread scan finishes, we calculate the time and time in seconds. That's it. So let's say cargo format again. I have to save this. Alright, yeah, it's I don't know, it's a VS Code issue, I have no idea. Yeah, so we are going to build it again. Now we have a multi-threaded scanner. So let's run the scanner with the same range of ports. Previously the output showed us that it did take 10 seconds. So now see what happens. See, the port scan finished within 1 second. So if you have some doubt on that, the impact of this one, this is not going to make any impact on this. If you have some doubt on that, we'll try to make use of that also. See, for 10 ports it just took only 1 second, and we got the port is open and the remaining ports are closed. So you may think this is going to be really good in terms of performance. Yeah, performance is really good, but it has an issue. Like if I say I'm going to scan from 1 to 20,000, let's see what happens. Yeah, it's faster. It's trying to do, see, it's not sequential, it's just, it did take only 7 seconds. And if you see, we got some port open. If you want to see really the correct result of this one, it's always good to comment this one out and build it again, then run it again. See, now we are getting only the actual port opened. So now it's trying to scan. See, it did take only 8 seconds for 20,000 scans. So till now it's really good. Like it's all good, working good. We are getting really ultra fast result. But as I mentioned when I was explaining the slide, it is very resource expensive. That means each thread is going to be created by the operating system, and each thread is going to have its own stack with its own memory. Is going to be the CPU is going to be allocated for the stack, for the thread. So in terms of resource, that is really expensive. So what happens as a result is that okay, make it 35,000. Just see what happens here. So now see, this is the problem. See, the entire actually my virtual machine that I'm currently running for this scanner has only 4 GB as RAM, and see, when it was going to be 35,000, I think Linux is by default is assigning 2 MB for all the operating system thread. So when it's going to be like 35,000 means actually it's very expensive, resource expensive one. So after a certain limit, what happens here is, see, it's not able to handle that, like because of the memory issue, it is not able to create more threads on that. So it just crashed. See, it is completely written from, see, entire stack got crashed, and it's all because of the resource expensive option that we have created here. So what is the safest way to do that? So there is another way to do this, to handle this one is, again, it's called like, it won't be crashed, but it is not a really good way to do that. But we'll move to the really an adoptable way of doing this one. So here what we can do is, instead of creating the thread like this, there is another method in thread. It's called thread builder. In thread builder, what's it suggests the stack size. This is the option for setting up our stack limit for each thread. So what I'm going to do is, I'm going to create a new thread, but before spawning the thread, I'm setting the stack limit. So it's not, I just want to make only 64. That's enough. 64 KB is enough because it's in byte. So I'm just setting it as 64 KB, and after that I'm spawning. So it's a new stack size. So here there is another difference. You have to call and wrap on this one, otherwise it won't get, the previous method was directly spawning without setting the stack size, but this one here we have to unwrap the result to get the handling. So did I make the mistake? Let me check why it is Oh sorry, it's the same name, multi-thread safe scan. So it should be working without any crash, even if you say the number of ports are really high. So I think this one will work. Let us call this function instead of, what is this? Sometimes VS Code's suggestions are really annoying. Yeah, let us rebuild this app. Yeah, now we did rebuild the app. Let's try the scan again. So I'm going to do the same scan, but this time we did limit the stack size, the thread stack size to 64 KB, and that option was here. See, we did set up the stack size here. Then, so here is the difference. Oh, again, maybe we need to reduce the stack, and this one we did 64-bit is again an issue. Okay, let me try with 25. See, for 25,000 is fine. Again, see, this stack size is not apt for my virtual machine, because my virtual machine has only 4 GB of RAM for the entire OS. So yeah, even for that, what I'll say, 64-bit KB is expensive for my machine. So up to 25,000, this is fine, but after that again it is getting crashed. So this is a scenario where we have to think about the other option. It's called asynchronous programming. So before jumping into that, let me show this one. As I said, threads are created by the OS, and in Windows, yeah, it uses create thread API. That all, if you are familiar with the malware development, you know what this function is. Yeah, when you are running the same thing in Windows, it's going to make use of create thread API, and Linux it's pthread create API, and there are some other stuff you have to note here. See, in stack size of default stack size of thread allocated in Linux is 2 MB, but I think the same thing in this one is 1 MB. But again, this is configurable, so these two values are configurable, so you can set it. So that's a difference of from a normal sequential application, sequential application to a multi-threaded non-sequential application. But we can't completely rely on threads, especially operating system threads. It is okay to some extent that like for operations like just I showed, up to even after setting up my stack limit, I was only able to run up to 25K. So suppose imagine you are going to scan the end ports from 1 to 65,536. So that port range is going to make big difference. So this multi-threaded scanner will never work on that. And again, if it's going to be a big machine, like if you have high configurable machine with a lot of RAM and CPU, so it's fine. But imagine if you are going to run it on a server with very limited resource, it's not going to work. So in this scenario, we have to think about the other way. It's called asynchronous task. So what happens here in asynchronous task is like, it is entirely different from from the threading pattern, like the other threading pattern. The other threads, when we created thread.spawn, it was calling the underlying operating system API. In Windows, it was create thread, and Linux, it was pt thread something, what I forgot. That was created, and it creates memory and CPU for every thread. But when it's going to come to asynchronous task, it's very lightweight. It's user space, and it's managed by a runtime. Actually, Rust doesn't have any default runtime to handle this. When I check, as per the old versions of Rust had the built-in green thread concept, like it had a built-in runtime that was handling that. But now it is mainly, this is the main runtime that is making use, is called Tokio. So how it works is like when you mark a function, and the main thing here is you have to, when you're going to use asynchronous task, you have to mark your function using the async keyword, and you have to use the Tokio.spawn method to create the task. Actually, it's going to create a future. I will explain what future is. As we can say, it's a promise of work. Tokio's runtime that runs all these futures on a single thread or a few, like it depends. And again, it has default values. So I will show the difference on that too. So we will be making use of that option too. That's I was explaining in the beginning. That was called Semaphore design pattern. So we can control the number of concurrent resources, and when you are going to make use of asynchronous programming. So this is called asynchronous programming, and more on this one. Theoretically, there are two types of threads. One is green and the normal thread. Green thread is, normal thread is created by operating systems. As I said, it has to. But the good thing about normal thread is, if you have multiple cores, actually the real parallelism will work there. Operating system is going to make use of the cores, different CPU cores, and it adjusts the threading stack based on that. But as I said, this was the issue. If you try to run it's very resource expensive. So if you try to run it on resource sensitive machines, definitely is going to crash. Your application is going to crash. Maybe it's going to affect all other applications running on the operating system. So never ever try to run these kind of applications on resource sensitive machines. You should be very careful about the threading applications. So green threads are another way. It's lightweight, user space managed. And why? Because it's calling green thread is actually green threads, you can say it makes use of the actual normal thread, and maybe under one normal thread there will be a lot of green threads. So all the green threads will be using the operating system threads stack and the CPU, all other resources allotted by the operating system. And very good example is Go routines, and it uses the same concept. Actually, it doesn't create any thread, operating system thread. Instead, it always uses the green thread concept. It make use of one or two or a couple of operating system threads to run a huge number of tasks. So it has a lot of but when you are going to say asynchronous task using Tokio, it is similar, but technically it is not. There are a lot of things happening behind the scene, and as I said, it's a future. It creates a future, and it's a lazy call. So when you future means is nothing but when you define a function using async keyword, and when you call the function, you just say .await, and that .await makes the function lazy, and the .await will wait until the asynchronous task creates a task for that. Just like thread.spawn, asynchronous, this Tokio has an asynchronous option that creates a task using the Tokio task spawn. I'll show you the example on that, so you'll get. The good thing is that just because it's going to create a bunch of operating system threads, but it creates a lot of green threads just by utilizing the very minimal level of OS thread that is created, the runtime creates. So it is scalable and performance oriented. So let's see how it works. So go back to our code. What we can do is, okay, here is a thing you need to refer. That's great. You need to refer the Tokio runtime, and the dependency is, yeah, definitely that's really annoying. Unfortunately, it doesn't have any other runtime. It has one runtime, it's, I think, STD. I forgot the name of that, but what to say, that ecosystem is very minimal. I think maybe in future they may include as a basic standard one inside this one. So I'm going to make use of this one in my cargo.toml file. I'm just going to refer. This is an optimal way of using it, like you can explicitly mention what are the features that you need from this one, but for the sake of making this faster, we are going to make use of all the features, and we have to refer the runtimes here. So so what we are going to do is we have to specify the same things like normal networking one. Yeah, there's a Tokio net TCP stream, and I'm just, yeah, this is a really good suggestion. I'm going to specify that as Tokyo's TCP stream because we already have one TCP stream here. To avoid the confusion, we just rename that as Tokyo TCP stream. So when we are going to make use of functions inside that Tokyo net TCP stream, we are going to directly use a Tokyo TCP stream, then the double colon. Then another thing that you may need is Tokyo timeout. Why? Because Tokyo TCP stream doesn't have the function like where is that, scanbout, yeah, it doesn't have the function like connect timeout. So we are going to explicitly use the timeout method, and inside the timeout method we are going to supply the TCP stream. So it's going to handle like that. So the next thing we need, I think with these two we can create a normal asynchronous function. So the first thing is async. So async. Oh yeah, it's going to say something. I don't know what exactly it is, but let us hope it is. We'll go through the code and we'll decide on what exactly it is creating for us. So this one is fine, but definitely we need to redefine the scan port, is because the scan port inside now the scan port is a normal function, so this is not going to work with the asynchronous function. The first thing you have to create is async scan port, yeah, name it like this. Let's see what it's doing. Oh yeah, it created actually, yeah, this is the thing that we need. Sometimes it's really, the AI is really good. What it's doing is everything is same up to here. So instead of TCP stream.connect timeout, what we are going to do is, as I said, it doesn't have this connect Tokyo TCP stream doesn't have the connect timeout, so we have to use of timeout method. Inside that we are just specifying the time, the timeout time duration. Then next is a future. Future is an asynchronous, I mean like the await anything that is making use of the dot await state, that is a call that we can call as a feature. What does it mean is like it doesn't do anything until you create until the runtime creates a spawn method. So it's just a lazy call. It doesn't do anything until it is called by some spawn method. So here we specify the timeout, and await is okay, it's fine, and this is an asynchronous function. So here we take here, and where was the synchronous? So it's not going to be handles. You can call it as tasks, and this one is correct. IP string is correct. No. And just a task, not handle. Anyway, here is the magic happens. Actually, here you say you have to mention it's not a normal move. Actually, you have to mention the async move, because the other one, when we were doing the thread spawn, we just use only the move function. We didn't mention the async, but you have to mention the async here, because Tokio is creating a task that is going to be executed by the asynchronous runtime. So as I mentioned earlier, it creates a couple of operating system threads, but inside just by utilizing that thread's resources, it's going to create a lot of green threads. So every task is going to have, just like the other one, is going to return a handle, but this one we have to mention async task. And so when you're going to call async task, you have to say await method, because so it just blocks till the function returns something. So await, and if the result is true, it's going to be this, and say task task.push. This is this task. So task in it is same as the handles of the other one, but just to the same things happens here. Instead of the direct handle dot unwrap that we were handle dot join dot unwrap that we were using for the thread, instead of that join, we are using the await method, and we ensure that all the tasks completes in this loop. So the async function, async scan is ready. Now we redefine our synchronous scan bot also, because the normal synchronous scan will not work with the other one. So we try to make use of timeout function of Tokio TCP stream to make it function like an asynchronous scan. So here again you come, the main important thing that you have to do is you have to mention your runtime here, Tokio main, and of course you have to make this function async. So this will do the work for us. So instead of this one, we will be calling async async scan port dot, and then just say await. So this should work. Let us see how it works. Oh yeah, this is another thing, because we have referred the Tokio. It's an external library, so it is going to take time. Did it build? Yeah, it's finished. It's good. It's more faster now. Did I update my rest? I forgot. Actually, there's a recent version. I think last week or something was just released. I did update my operating system, but I'm not sure I did update, and there is. I have to check it. Okay, whatever it is, we are going to run the scanner again. See what happens. See, it completed in 3 seconds, and if you did it, it is 2 seconds difference, but it's not going to be the same every time. But the major thing that we have to test is this one, because the multi-threaded, even after setting up the stack size, it got crashed on 35,000. So okay, let us make it as 65,000. 536. 1 2. Yeah, anyway, the range is going to take 1 minus, so oops. Oh, that got panicked. Oh my god, what was that? Okay, let's test it. Okay, I think it is because of the range. Yeah, because we are using unsigned 16 integer for the port range, so let's see this one. Yeah, this is fine. The 536 was actually out of range, I think. So for this one, I want to see how many seconds. See, it completed within 13 seconds without crash. That's a major difference between the multi-threaded application that we tried. We tried the multi-threaded application in 2 different ways. Like we tried with the setting up. We tried the normal one. We were creating for each port. We are creating each thread to do the scanning. That crashed. I think even 25,000, 30,000 or something. Even the 20,000, I think it got crashed. Then we set up the stack limit as 64 KB. Then tried again. So up to 25,000 or something, it was okay. But above that, it was again got crashed. But here there's a major difference. Like even we set up the 65,000 as range, and it did finish within 13 seconds, and it didn't get crashed. Why? Because this is a concept of a kind of green thread, but yeah, technically it's not complete 100% green thread. But behind the scene, what happens is he's trying to get some create some OS threads, but just by utilizing the same resources allotted for those OS threads, it creates multiple green threads to work for the scanning. And just because it's an asynchronous scan, it just blocks time consuming operations, and just go for the other one that's available, then just work parallelly and just get the result. And yeah, that's the result of this. So but this one is, again, it has some technical issues. So this is good. Even this one, up to this one, is really good. Asynchronous, you can make use of it. But in a real-time enterprise network, this is going to be very loud and noisy. So what happens on that side is, like, I think, yeah, even though it has low resource usage, if it's 10,000 tasks is very tiny for the no thread explosion. Yeah, you just saw it. There is no true parallelism, and unless you mention multi-threaded runtime. I have never used this option. But again, it's very loud. It doesn't have any control over the number of concurrent threads, and this is a major difference between the green thread and normal thread. The main issue is this one, stack size plus the context switching cost. that's designed by the operating system is happening on the normal thread. And when it comes to asynchronous, it's a kind of similar green thread concept, but it is not actually green thread. But yeah, you just saw the result, the difference between the normal threading and asynchronous threading. And see, we just saw this range, and he did within 13 seconds. It was absolutely fine. And definitely, if you try this in Windows, it may take more time. You can try that in Windows if you want. And yeah, definitely needs another runtime, and number of concurrency we can't control. At present we are not controlling that. So the next best option is another option is called Semaphore design pattern. So what is a Semaphore design pattern is, in a Semaphore design pattern, actually here in normal asynchronous application, even though the threads are really effective, but we don't have any control over the the number of concurrent green threads that's going to be run on the machine. So the very effective way of controlling that is called Semaphore design pattern, and every programming language has that design, some design pattern. So some provides, Go has a different way of doing it. It has synchronization channels to handle that. But in this one, this Tokio runtime is helping us to do the design pattern. So what happens in that design pattern is, again, is a synchronization primitive. Like we are doing some synchronization primitive inside the asynchronous programming. We says this is a this is a option that is given by Tokio to do the Semaphore design pattern. Is really very effective design pattern when we are going to use thread, especially if you're planning real-time threaded multi-threader asynchronous application. This is a must, because till now all the multi-threader stuff we did, it is really useful when you are doing CTF style tasks, but it may not work on enterprise level, because enterprise level we need to control your resources based on your need. So definitely this is a highly recommended design pattern for that. So normal asynchronous, actually how it works, it spawns an asynchronous task for every port. See, 100 tasks for 1,000 tasks for ports from 1 to 1,000, and the runtime actually schedules a task concurrently on a single thread. Normally happens by default, running as many as possible at once. No explicit limit tasks. Start immediately and run until completion of timeout. So it's constrained only by system resources and the runtime scheduler. For our scanner, theoretically it start all at once, and internal scheduler is handling that. So, but we don't have any control over this. Like we are not specifying any concurrent number of concurrency on that. But when it comes to Semaphore pattern, it make use of Tokyo's sync Semaphore. See, you have to mention. You have to be very specific on this one. Is a synchronization pattern that controls the asynchronous running of the Tokyo runtime to limit the concurrent task. So you can specify a number of concurrent tasks. It has a lot of good things, but definitely is going to be slower than the other uncontrolled asynchronous one, because when we are trying to say 10 threads, or not threads, actually 10 parallel tasks at a time, we are restricting that behavior of asynchronous task. By default, asynchronous task is taking like if it's 1,000 ports, it may have 1,000 tasks to run at a time. So it will be definitely going to be faster. But when it comes to Semaphore, it will be slower, but you can say you don't, even for asynchronous, as I said that it makes a lot of noise on the network if you are going to do that, because of the number of the concurrent tasks you're running will be really huge on the machine. So that activity is actually very loud. So in a real world pen testing scenario, this is a thing, like say I'm just blasting 10,000 ports. Is really good for when you're doing like CTF style stuffs. But see here, in a real world scenario, the Semaphore design pattern will help you to be stealthy, not stealthy, but to be like a very less noisy intruder compared to the other stuff we have seen till now. So for implementing that, what we need is, as I mentioned, we need that use Tokio runtime Tokio sync Semaphore, and we may need to redefine our, we have to define another function. That's a better option. Just keep the asynchronous port scanning just like that, but for the Semaphore one, we are going to control the entire number of concurrent tasks that are going to be run. So what we can do is, we're going to say async function Semaphore scan Semaphore scan the parameters. Yeah, just copy the parameters. I don't know why AI is not suggesting us these things. Let it be the same set of parameters. And here yes, I forgot to mention one more thing. We have to make use of another thing for this one. It's called arc. Arc means actually, yeah, let me say, yeah, this one. It's called atomic reference count, and I think I had a slide for that. Yeah, before that I forgot to explain this one. I referred this in between. We were talking about the synchronous thing. I already explained, I think. A future is just is a value that represents a work that is not yet finished. So, and it's kind of promise that will be available later, and it's kind of to-do list that is handled by the rest. The core idea is it's a building block of asynchronous programming in Rust, and they don't do anything on their own, and you need a runtime just like Tokio. So to run them by polling, that's a design by design. It is polling until they are complete. So they are lazy, as that I already mentioned, and it won't do anything until you call using the Tokio spawn. So when you're calling that Tokio spawn, it's telling Tokio that here is a future, you have to run it for me. So the runtime keeps checking the polling until it in our case, until the connection succeeds or timeout. That's how it works. That's a future is. So come to this one. Yeah, here it is. Arc. It's called atomic reference counting, and it's a thread safe smart pointer in res that lets multiple parts of your program share ownership of the same data across threads. So if you have something in Arc that will help you to share ownership of that one, the data between different threads. Why that matters is because as per the design of Rust, actually it just allows only one owner for one particular variable. The ownership must be only by one function, or when whoever is going to call the function, it should handle the reference properly, the ownership properly, because if that's the core of this Rust. That's how it handles the memory safety. That's why it doesn't have any kind of garbage collector with it, because that ownership pattern will deal all those things. So what happens here when you're going to use Arc is Arc makes sure that you can handle the ownership in a thread safe way. So it doesn't allow your data is going to get crashed just because of the ownership issue. So you can just create ownership using the Arc. So you can place any data type inside the Arc. So it doesn't matter. It doesn't be very restricted to any specific type of data type, but you can add anything to Arc. So it will be available for different threads by keeping the ownership safely without crashing it. So you have to always use arc.clone. So whenever you're going to use arc.clone, it's going to create a reference, and that reference is always incrementing the count. Then so whenever the arc goes out of scope, the count decrements, and whenever it's going to reach 0, the data is deallocated. That's how it is handled in between. And there is another one called RC, that is called normal reference counting, but is not designed for thread safety. So try to use Arc whenever you are trying to use data that is needed to share between threads. And if you really want to use your data that is need to be mutable, then you have to use the Arc mutex. But in the Semaphore pattern that we are going to use, we don't need to do any kind of update on the data, so we just use immutable. I mean, like, we don't need to change anything on the Arc variable that we are going to make use. So here in this design pattern, Semaphore needs to be shared across all the asynchronous tasks that's going to be created. So each task on its own spawn context when you're going to call the Tokio or spawn. So definitely it's going to execute different thread. It's going to be executing different threads in a multi-threaded Tokio runtime. Even though Tokio is actually creating kind of green threads, but as I mentioned in the beginning, it always make use of some kind of at least some of the operating system threads. So keep always that in mind. It make use of that threads resources to do all these actions. So when you're going to say Semaphore.clone, it gives each task a handle to do the same Semaphore, so incrementing the arc count. So when you're going to say your Semaphore.clone, we just increasing the atomic reference count and passing that reference to the task. And what happens here is that without Arc, you can't share the Semaphore safely on multiple threads. So how it controls the concurrency is that the Semaphore itself limits the active number of tasks to this is an example, to the number we set via a method called permits. So Arc ensures that all the tasks can safely access the Semaphore to request the permits, even if they run concurrently. Arc makes sure that all these threads can safely access Semaphore. So when we set call a semaphore.clone, and when we set a maximum number for this concurrent task, what happens here on the semaphore pattern is it limits number to the specific number that we specify, and it will never allow any concurrency that goes beyond that. So it just limits it with the number that we set. And when each task finishes, the semaphore clone is dropped, so it's decrementing the count. Then after all tasks complete, it hits 0. Then the semaphore is cleaned up. Again, actually, it's kind of, after every task is cleaned up, semaphore is coming back to 0. Then again, when a new task is spawned up, it allows another set of tasks up to 10. Then it says if it's filled with 10, suppose imagine 10 as a number that we set, it fills up with 10, then it instructs the runtime to wait until all these 10 tasks completes. Then again the count goes to 0. So it's like every time there will be 10 concurrent tasks. So if the concurrent task is not 10, then it allows to add concurrency up to 10 every time. That's how it controls. So to make this working in real time, we need to make use of these things, and the pattern that is going to work with this one is different. Let me copy this code to here. So what happens, we have to make some changes on the threading pattern for the semaphore design pattern. So this one is fine. We are going to define one more thing here. It's called as max task or something. That's equal to just say we'll start with 10 and we'll see how it goes, and just say it is 10, and it says this is really good. This is a way we are creating a new arc, and it's a semaphore type, and it's a new with max task. So we define that. Now inside this the port scanning work that we are going to do, we have to control this. So where to control this is, we have to mention it here. Let's say let set permit semaphore clone acquire, await, and unwrap. This is a magical line that is going to control this asynchronous task. So what happens here is, as I mentioned, it allows this kind of gatekeeper, like so this line just blocks it, and when you say 10 maximum task, it allows to create 10 tasks, and the reference count will be going down whenever the task finishes. So whenever it reaches 0, again it allows another 10. So when it reaches 0, another according to the main loop that we use, it checks the reference count and allows the number of patterns. So it will never go beyond 10. So now we have that one. Apart from that, it doesn't have any other things to do here. It is saying some issue, semaphore.clone. Current and wrap. What? is the issue on this one? Temporary value dropped while borrowed. Consider let is bring a create longer lived value. So we did create inside the loop, and we are checking the task here, and what was that issue? I didn't get actually what. Okay. Oh, okay. Okay, you have to. Okay, this is not that clear actually. The method was changed. Actually, I used the wrong method. Acquire owned. Let me see this. Yeah, we had to. Yeah, that's a diff. See, these are the rusty ownership things that you should be always be careful of. Now, it's nothing but we just ensure that the value is not going to live longer than that we defined. That's it. So try to, okay, we had to call this method, right? Semaphore scan. Now the asynchronous task is same, so we just call this method now. Yeah, it should be await because it's asynchronous, and we're going to build it again. So now it is done. Let us try to run this scanner. Yeah, try with this one. See, it's kind of batch it is running. So what happens here is it's just trying to limit the number of asynchronous tasks. So even this didn't take much time, just took only 13 seconds, but I think for the other one also it was only 13 seconds, so it didn't make any big difference here. Okay, one more thing, I think it will make the difference. I forgot one thing. Yeah, why? Because see, when you create this task, okay, we have created the permit is here, so now theoretically actually this permit will drop off after a scope, but when I was trying to use in my other applications, so this makes me, this line makes a lot of difference. So we are explicitly just dropping it here, so definitely on the next build you can see the difference. Let me see, it should be, the number of seconds should be more than the normal asynchronous task. No, yeah, let it be. See, only 1 second is different, but yeah, definitely. And now the biggest advantage is that now we know how many tasks are running parallelly, asynchronously by the runtime. So now we limited this one to 10, but you can just try to make use of 100 because to be more efficient for this case. Just try the same thing, but in this case for a single scan it won't make any big difference, I think, but still it is. One more second, 15 seconds from 10 to 100. Yeah, definitely it's not because of the concurrency thing, but it might be some other network latency or something else. So whatever it is, we know this concurrency is limited. We are controlling that using the number of concurrent threads using this semaphore design. So this line ensures that it will never go beyond the number of maximum tasks that we set here on the synchronous Tokio runtime. So these are the different patterns that you can try when you are developing a serious application using asynchronous or multithreading. And when you say multithreading, you should be very careful. As I shown in real time, it has a lot of issues that you need to handle. Even though you may feel it as it is faster, but definitely have to keep one thing in mind, that it is always resource expensive. So don't try to run a bare multi-threaded application like an OS multi-threaded application in a very resource sensitive machine. Always try to make use of asynchronous, and I strongly recommend to make use of Semaphore design pattern, so you can control the number of concurrent threads in your pattern. So it will help you to do more control over the multi-threaded or asynchronous. I mean, asynchronous is multi-threaded in a way, but it doesn't create OS thread like the normal multi-threaded applications. So there are some other things in threading that is called channels in Rust that I will cover in another video. This is already a very long video. So the thread channels and another package for parallelism is there. So those things we will cover in upcoming videos. So I hope you enjoyed the video. This was a really deep dive into the threading patterns. I haven't seen any kind of useful threading examples anywhere, because everyone is using just some print statement and just explain what happens behind the scene. It was really a big task for me to do all these things, but now I'm getting familiar with this one. I'm just trying to implement in my own projects. I'm trying to implement all these things in my own projects. That's how I learn. And yeah, whenever I share these things with you, I learn more, because when I make mistakes and I'm coding again, so it helps me to learn more stuff. So that's all for this video. I hope you enjoyed the video. If you are seeing this first time, I strongly recommend you to go and visit the previous videos to get a grip on the basic Rust. Definitely we will be redoing the web application scanning options in another using asynchronous programming, but we'll combine all the scanning options that we did, and we're going to create one big project using the async programming. We'll be doing that in upcoming videos. So that's all for this video. See you soon with another one in Rust. Happy Rust coding and happy hacking with Rust.